This is the video for Unit 8, Lesson 7, Linear Programming. So the goal is we're going to introduce linear programming, which is taking what we've learned about systems of inequalities and applying it to real-life situations. So linear programming is going to use something called an optimization technique. So we're going to use what we've learned about systems of linear inequalities to determine a maximum or minimum to either maximize a profit or minimize a cost for a situation. So our first step is we're going to define our variables and write inequalities. These inequalities are going to be restrictions or constraints for a problem. And we're also going to identify something called an objective function. So that's our function we're going to use to determine a maximum or a minimum that we want to use. When we graph our inequalities, our solution region where all the shading overlaps, that's going to be called our feasible region. And the intersection points where all of our inequalities overlap and the vertices that form that region are going to be called our critical points. We're then going to test these points using the function we developed to determine if a maximum or minimum, depending on what we're looking for in the problem. So our first example here says Erica makes party supplies. She wishes to display her product at a convention so that she can get the maximum number of inquiries about hats and whistles. Her booth at the convention has 12 square meters of floor space to be used for the display purposes. A display unit for hats requires 2 square meters. A display unit for whistles requires 4 square meters. In Erica's experience, she would never have more than a total of 5 units of hats and whistles on display. If she receives 3 inquiries for each unit of hats and 2 for each unit of whistles, how many should she display to get a maximum number of inquiries? So lots of things going on in this problem. The first thing we're going to do is just simply define our variables. What are the 2 things we're looking at? It says that she wants to get a maximum number of inquiries about hats and whistles. So we're looking really here at those 2 things. So I'm going to let X be the number of hats and Y be the number of whistles. We then have our different constraints that for these problems. So we are going to have one constraint is that the hats, we know we're not going to have negative hats, so we're going to have X is greater than 0 or equal to 0. We're going to have a constraint for Y, so Y is greater than or equal to 0. We also have some other inquiries or some other inequalities we can write here. So it gives us some restriction on like the size of the space. So she has 12 square meters of floor space for her display. So each hat is going to take 2 square meters. Each whistle is going to take 4 square meters. So we can go ahead and write an inequality for that. We could say 2x plus 4y cannot be great. The most it could be is 12, right? That's how big her space is. So less than or equal to 12. We also have another inequality we can write. She would never have more than 5 units of hats or whistles displayed. So if I write that out, I have X plus Y is less than or equal to 5. So the most she'll have is 5. We then have an objective function we can write. So after we find our constraints, it says if she receives 3 inquiries for each hat and 2 for each whistle, how many should she display to get a maximum number? So we're going to maximize it, and I'm going to make you say profit. And so we're basically going to say an X and a Y. We're eventually going to put coordinate points in there. And it says that she gets 3 for hats and 2 for whistles. And so the objective function we're never going to graph. we just use it to evaluate points. So now we're going to go ahead and simply graph these inequalities. So I'm going to rewrite these in slope-intercept form. You don't have to rewrite them in slope-intercept form. You can graph them in the other form. That's fine. But we have for this one, if I rewrite it, this is going to be y is less than or equal to negative 1/2 x plus 3. So that's like, again, just solving for y. Same thing for this one. This would be y is less than or equal to negative x plus 5. And then I have my other inequalities here. So the graphing we saw in the previous lesson, so if you want to take a moment to try to graph it, I'm going to show you what the graph looks like so you could see if you graphed it correctly. This is like what you saw in the previous lesson, graphing a system of linear inequalities. So the graph should look something like this. And you have this purple region here is this shaded region where we kind of formed like this quadrilateral, and these are the vertices for that quadrilateral, right? When we graph this, we have our critical points. We have a point of 0, 3. We have a point of 0, 0. We have a point of 4, 1, and 5, 0. So those are the vertices, or our critical points. We're now going to go ahead and put that into our objective equation to see which of these gives us the maximum number of inquiries. So if I put all those in, 0, 3, I'm going to put in 0, 0, 4, 1, and 5, 0. And we're just going to evaluate. So I'm using this objective function. So 3 times 0 plus 2 times 3. 3 times 0 plus 2 times 0. 3 times 4 plus 2 times 1. And 3 times 5 plus 2 times 0. And the different values we get. So 6, that's 0. That's going to be 14, and this is 15. It said we wanted to maximize. So my greatest value is actually 15, which means that the 0.50 gave me the maximum number. So that was, we defined that was 5 hats and 0 whistles. And that would be it. For example 2, similar situation that we're going to use a system of linear inequalities. We're going to do the same steps, but we might find that we're looking for a different value. So example 2 says the owner of a pet store plans to purchase some hamsters and rabbits. They decide to spend at least $100 to purchase 8 animals. Each hamster costs $5. Each rabbit costs $25. Suppose that it costs 13 cents a day to feed each hamster, 30 cents a day to feed each rabbit. If the daily costs are held to a minimum, how many hamsters and rabbits should be processed? So if we go ahead and define our variables first, we have that we're looking at hamsters and rabbits. For the constraints, same as before, we're going to have x is greater than or equal to 0. We're also going to have y is greater than or equal to 0. So we can't have negative hamsters or negative rabbits. And then we have that we want to spend at least $100 to purchase 8 animals. So they give us a quantity and a value. So each hamster is 5, each rabbit is 25. So I would have here 5x plus 25y. The smallest this would be is 100, so greater than or equal to 100. And then for the number, I know the number of hamsters and rabbits, the smallest it will be is 8. So when we go ahead and then write also our objective function, they tell us that it's 13 cents a day to feed a hamster, 30 cents for a rabbit, and we're trying to hold it to a minimum. So that's a little bit different than the last one. So we're actually more looking at cost. So I'm going to use C instead of P, but it really doesn't matter. So I'm going to write this as 0.13x plus 0.30y. We're now going to go ahead and graph this out. I'm going to rewrite it in slope-intercept form by solving for y, but again, you don't have to. I'm going to skip the steps to show that, but you would have negative 1/5 x plus 4, and then this one would be y is greater than or equal to negative x plus 8. And then we have our other inequalities. So I'm going to give you a moment to try to graph it yourself and then identify the critical points, and then we're going to evaluate. So when we go ahead and evaluate this out, this one's a little different. So the shaded region you can see is this region that is, the last one was a region down here. This one, we can see where when we shade it, we only have 3 critical points. So these are our 3 that we're going to look at. We're trying to minimize the cost. So when we take our objective function and evaluate, we're looking for our smallest value. In this case was $1.55. So 5.3 actually yield us the smallest value. So in order to minimize costs, they would want to have 5 hamsters and 3 rabbits, because that would give you the smallest value, because since we're looking to minimize. And that would be it. So if you have any questions, you can ask during class, sign up for T-Bolt time, or go to the center.